Recall that our plan this week is to talk about sequences, series, and power series. We have some short definitions of what a sequence, a series, and a power series is. A sequence is a list. A series is a sum. And a power series is a function in the form of a polynomial, but with infinite degree. That's the weird part. For all three, we have a different question. And that question surrounds convergence. A sequence converges if the terms have a limit. A sequence is the simplest object. It's just a list. And a sequence converges if the terms have a limit. A series converges if the sum is finite. A power series has a different style of question. We want to know for what values of x does the power series converge? When we take a real number as an input in a power series, the output is a series, and we want to know what inputs lead to a convergent output. So in a power series, we take as an input a real number, and the output will be a series. And the question that we have is, for what values, for what real numbers do we get a convergent series? So for a power series, the question is, for what values of x does the power series converge? These are the objects, and these are the questions concerning those objects. The reason that we care about series is that when we plug things into power series, we end up with a series, and we have to know if that makes sense. If we have to know if that series converges or diverges. And we have to know right away. We have to know just by looking at it and knowing the characteristics of a convergent series. The reason that we want to do this is that we can use power series to model functions. The reason that we care about this whole process, sitting behind all this, is that we can use power series as a model for a function. So we use power series as models for functions. One of the things that we want to do with all this is to use a power series as a model for a function. This is because this means we can approximate a function with a power series, or sorry, a polynomial. The power series has the form of a polynomial, but it has infinite degree. It goes on too long. So at a certain point, we want to stop writing terms for our power series and use that as a model for our function. We want to understand this process better. This is important because we have some functions that are transcendental functions that are very strange in the calculation and very strange in the behavior, but polynomials are super simple. Polynomials are all based on addition and multiplication and exponents, but if you're based on addition, multiplication, and exponents, you're pretty much just working with addition. Multiplication is just repeated addition. Exponent is just repeated multiplication. Sitting at the bottom of that is just addition, the simplest of all of our operations. So if we could take some weird function like e to the x and model it with a polynomial, then we may gain something. Also recall that there are some, one of the processes we learned, integration, there are some functions that don't have nice antiderivatives. We don't have an antiderivative that can be represented with a finite combination of elementary functions. So for example, e to the x squared does not have a nice antiderivative. We can represent the antiderivative of e to the x squared with a non-elementary function. That would be the second fundamental theorem of calculus. Use that to construct an antiderivative out of the definite integral. So we're using a non-elementary function. The other part of that was the finite part. We can't write the antiderivative as a finite combination of elementary functions. So we can use an infinite combination of elementary functions as a model for our antiderivative. All right. Let's talk about series. The structure here is that very much one thing leads to the other, which leads to the goal of understanding power series. We want to understand power series, so we need to understand series. To understand series, we need to know something about sequences. And that's going to start at the beginning when we talk about convergence of a series. So let's consider a series AN. We want to know if adding up this infinite number of terms is finite or if it's infinite. One way to do that is our favorite brute force approach. So we want to know if the series AN converges or if the series AN diverges. That is, we want to know if the sum of all these ANs is finite or if the sum of all these ANs is infinite. So let's talk about our brute force approach. So the sequence of partial sums is our brute force approach to determining if a series converges or diverges. So brute force in math is when we just decide to start trying stuff. So if someone's got a 4-digit PIN code, a brute force approach would just start with 0000, 0001, 0002, 0003, 0004, and so on. This is why I only get so many tries. Like if you're playing Wordle, a brute force approach would just be going down the list of things that would fit. Side note, Wordle hard mode is actually not hard mode. Wordle hard mode is actually, in certain situations, will force you to guess and could make the game unwinnable. So Wordle hard mode is not necessarily harder. It could make the game unwinnable because of luck. Just as an example, at one day, the Wordle word was watch. There are 7 words that end in ATCH. Match, batch, watch, catch, hatch. I didn't do them in order, so I don't know if I said this, but watch, patch. That means even if I told you on Wordle that the word ended in ATCH, in hard mode, you have to guess with ATCH, which means you can't win. You can't do the smart play of come up with a word that has a bunch of choices of your first letter to figure out what the first letter must be. That's the smart play. Hard mode says, no, 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 you have to guess. It requires luck. So bad design on hard mode. The smart play, when your number of choices exceeds the number of guesses you have remaining, is to narrow down with something different. So that's bad game design. It doesn't come up very often, so no one cares. Also, there was one day when I missed the Wordle word, and you can guess what the word was. There are 7 guesses to choose from. What are we talking about? A brute force approach. So what this means is that we're going to construct a sequence of partial sums. It's like right in the name. So the sequence that we construct is the first term is just the first term of the sequence. The second term of the sequence would be the first 2 terms, A0 plus A1. Then the next term, A0 plus A1 plus A2. And we just try to determine if this sequence is going to have a limit. We just keep adding terms. The limit of this sequence will be the sum of the series. If the series converges, if the sequence converges, then the series converges, and the limit of the sequence will be the sum of the series. So notice that the way we build the sequence of partial sums is we just take the previous term and add the next term to it. So the next term is based on the previous term. Or the previous term. So we could define this sequence of partial sums recursively. I could start off by saying S naught or Sn, the nth term of the sequence is the previous term of the sequence plus the next term. The nth term is the previous term in the sequence plus the next term in the series. Now we have to tell the reader where this all starts. This says take the previous sum and add the next term. So we have to tell the reader where this starts. So we say the first term of this sequence is the first term of the series. So S naught is A naught. S1 will be S naught plus A1. S2 will be S1 plus A2. S3 will be S2 plus A3, and so on. So this is another way that we define sequences. Define a sequence of terms, a sequence in terms of early terms. Here is a famous sequence. It's a S naught is 0, S1 is 1, and then the next terms are just the sum of the previous two terms. So S2 would be S naught plus S1. So 0 plus 1 or 1. S3 would be S1 plus S2. So 1 plus 1 or 2. S4 would be S2 plus S3. So 2 plus 1 or 3. So our sequence will look like 0, 1, 1, 2, 2 and 1 is 3, 3 and 2 is 5, 5 and 3 is 8, 8 and 5 is 13, and so on. This is our most famous recursively defined sequence. And it is usually the first example in the first sequence. That's why when you see the part of some. Everybody just always goes for Fibonacci. This is analogous to the XKCD topic with Zombie-Murray theory. Yesterday, we saw that when we made a sequence of 3 plus 2n over 7 plus 5n, we had a limit. So the sequence where Sn is 3 plus 2n over 7 plus 5n, that does converge. It converges to 2/5. But what happens if instead of making a list, if we turn this into a sum? So recall the sequence Sn equals 3 plus 2n over 7 plus 5n for n greater than 0 converges to 2/5 since the limit as n approaches 0 or approaches infinity. But this is a series. I'm not just looking at the terms and seeing where they're headed. I'm trying to add up all these terms. We're adding all the terms, not just making a list of the terms. Not 3/7, 5/12, 7/17, so on. It's 3/7 plus 5/12 plus 7/17 plus 9/22 plus 11/27 and so on. So we could try our brute force approach, 3/7 plus 5/12 plus 7/17 and 9/22 and 11/27. But it's going to be kind of a while before we see this level out, if it's going to level out at all. Fortunately, we do have computing power. Anytime there's a brute force approach and we're looking at a calculator, we got to ask ourselves, I wonder if there's some faster way to do this. And right underneath FNINT is summation. And let's see, I want 3 plus 2n over 7 plus 5n. The notation requires us to put in the expression comma x, comma 0, comma, and I did see 0, 1, 2, 3. So 0, 1. So it looks like we typed it in right because our 9/22 and our 11/27 both added up to the right amount. You might notice in our syntax here, I put the function comma x, comma 0, comma 4. And this syntax is very familiar to the one right above it in the math menu. And if you're thinking, this seems an awful lot like integration, that's because this is an awful lot like integration. Integration is just adding things up. And what are we doing here but adding things up? So if we're going to explore this in brute force style, we're just going to keep plugging in, adding up more and more terms. And it certainly seems the more terms that I add, right now the calculator is mad at me. It's like, oh, come on, man, 1,001 terms? Son of a. This evidence suggests that if we add more terms, we just add to the sum. Oops. So when we had up to 11 terms, the sum was 4.5. 101 terms, the sum was 40.5. 1,001 terms, the sum was 400.7. And so even though we have not got to very large values of n, we're only looking at 1,000 terms, the data seems to suggest that the sequence of partial sums diverges. Since the sequence of partial sums diverges, we would conclude that the series diverges as well. Let's think about this structurally and see if that makes sense. Let's think about what's going on. So we don't have to ask our calculator to do 10,000 terms. Right now the calculator's like, oh, come on, man. I'm gonna put that aside. See how long it takes. So Wow, it still doesn't have it. Let's think about what happens. Remember that we know that the sequence converges to 2/5 because for large values of n, these terms are going to be arbitrarily close to 2/5. So it's still working. What this sequence looks like in the long run, at a certain point, the terms become arbitrarily close to 2/5. For a large value of n, for large values of n, the terms in this sum are arbitrarily close to 2/5. Still hasn't got it. It'll never actually look like 2/5 plus 2/5 plus 2/5. But at a certain, for large values of n, those terms will be arbitrarily close to 2/5. Unsurprisingly, it went up by another factor of almost 10. So it finally got it. 10,000 terms, it went up to 4,000. So it makes sense that our sequence of partial sums is going to diverge because we're just making a sequence. The next term of the sequence is going to be 2/5 the previous term of the sequence. For large values of n, the terms of the series are arbitrarily close to 2/5. I don't know why I picked 1,000. It's not even very large. But anyway, for large values of n, the sequence of partial sums will be like, we'll have some 1,000th term. The 1,000th first term will just add 2/5. The second term add 2/5 again. The 1,003rd term will add 2/5 again. We just keep adding 2/5. This will not level off. If we keep adding 2/5, the terms will not level off at some limit. If we keep adding 2/5, the terms will not stop growing. Therefore, the sequence of partial sums diverges. Therefore, the series diverges, as a series converges or diverges based on the sequence of partial sums. Also note that most of these fractions are close in value to 2/5. So if we have 1,000 terms and they're all close to 2/5, 1,000 times 2/5 is going to be about 400. 10,000 times 2/5 is going to be about 4,000. A little bit more because some of the terms are bigger. So we're not surprised by this at all. It makes sense that since the terms eventually just add 2/5 and add 2/5 and then add 2/5 and add 2/5, the sequence of partial sums will diverge, therefore the series will diverge. So now we've come to the first thing we want to recognize about series. It still hasn't got 20,000. This is going to be the first thing we look for to decide if a series converges or diverges. Referred to as the test for divergence. Let's let A n be a series. If the terms don't go to 0, the series diverges. If the terms of your series do not go to 0, then your series diverges. If the limit of the terms of a series is not 0, then the series diverges. This is our first stop in identifying whether a series converges or diverges. We check to see if the terms go to 0. If the terms go to 0, the series diverges, and we're done. I'm sorry, if the terms do not go to 0, then the series diverges, and we're done. Note that this just says if the terms don't go to 0, then the series diverges. The only thing that we get from that with converges in it is the contrapositive, which says if a series converges, then the terms go to 0. But that's that goes in one direction. If the series converges, then the terms go to 0. Note that the if then placement. If a series converges, then the terms go to 0. We do not get the other direction. If the limit of the terms is 0, the series could still diverge. That's the most important thing to realize. We'll see some examples of this with some further tests for convergence. But if it was just as simple as the terms going to 0 include convergence, we would be done with this whole section on convergence instead of having all these wacky tests for convergence. So you don't get to turn this around and saying if the limit of the terms is equal to 0, then the series diverges. A implies B does not imply not A implies not B. A implies B implies not B, then not A. Everybody remember that from your logic course? I'm kidding. No one takes a logic course. I'm not sure we even have one in the district. I know there's one on the book for someone at CSM, but that was many years ago. That was actually decades ago. I can measure that in decades. All right. That was like 30 years ago. So tomorrow we will continue talking about determining if a series converges just by looking at it. That's going to do it for today. I'll see y'all on tomorrow, but have a good day and thanks for playing.